All right, so you're here for the set 1 questions for the AP Physics C Mechanics exam of 2023. My hope is that by going through this video of the set 1 questions, you'll be able to get an idea as to what sort of score you may have gotten and how well you may have done on the exam as well. Remember that typically a 5 on the mechanics exam could range somewhere between 52-ish% to about 60-65%. There's kind of a big range depending on the year that you're at. So, if you don't feel like you did too well on the FRQs, keep the faith. You may have done pretty well on the MCQs as well, and that could also heighten your score quite a bit as well, too. And, if you did very well on the FRQs, that's a good sign that you've at least passed this mechanics exam. All right, so taking a look at question 1, we have a block. That block is on a spring as well, too. We do compress it, and then that block is going to go up the ramp. So let's go on to the next page then. All right, so we do have this graph right here comparing 2 different spring forces as a function of position, and we are asked to go ahead and graph the different spring forces as well. So based on this free body diagram, we can go ahead and graph quite a bit. I'm going to go ahead and start my annotations right here, and I think that it should let me do. Okay, there we go. So obviously in both cases we have the same block, so both blocks are going to experience the same weight force pointing down because they have the same mass. Accordingly, they should both also experience the same normal force, and those normal forces do have to be the same length as your weight force to get full points. So that's very important. In addition to that, both blocks are going to experience a spring force, but both of those spring forces should be different lengths. Trial 2 with spring Q has to have 1.5 times the spring force as in trial 1 with spring B. How do I know that's going to be 1.5 times as large? Well, if you go onto the force time graph at the time 0.1 where is it? 0.01 meters, excuse me. What you should actually see, and I actually read that wrong, I apologize, but at 0.01, right, you should have 1 Newton of force and 2 Newtons of force. So let me actually go ahead and erase these. Sorry, it should not be 1.5 times as large. You should have trial 2 is actually double as large of the spring force. So it did decide to go to erase my vertical forces. Let's go ahead and put those. And let's say that for trial 1, the spring force is 2 squares. And then for trial 2, we can put it as 4 squares just to make those a little bit more visible for you guys. Again, trial 2 should have double the spring force that trial 1 does based on the graph. All right. Now, if we go ahead and we do take a look at part B is asking us which features of the graph could be used to estimate the work done by each spring as they are compressed. And it's just going to be the area. So it's going to be the area of a force time graph gives us the work done. So the area under the graphs, and that's going to be from that's going to be between x is 0 and x is equal to 0.1 meters. 0.01. Sorry, I keep missing that 0 there. 0 and 0.1 meters. All right, there is one compression distance where the max height reached by the block is the same. Predict how that's going to compare to 0.04. It should be greater than. The distance where the 2 heights are going to be the same should be greater than 0.04. And the reason why is because the area under both graphs, and I apologize that my pen is going slow. There's a little bit of lag in the inputs, but hopefully it's not really detracting too much from your understanding here. The area under both graphs would be the same. Would be same after that point. And the reason why that's important is since energy is conserved, because there's no friction, right? Since energy is conserved, what we need is work done to be equal, W equal for both. masses implies that UG and therefore H max is going to be the same for both blocks as well. Good. All right. On the third part, what we have is we're asked to graph the spring force, the maximum height as a function of x for both of them. Well, the way that we would actually figure this out is we have to figure out how gravitational potential energy does depend on the spring force then as well, and how it depends on distance. The way to do that is because we know gravitational force is equal to work done, and work done is going to equal the integral of f dx from 0 to x then, right? So for spring P, what you should end up getting is the classic 1/2 kx squared, right? But for spring Q, if you go ahead and you do the integration, you'll actually get 2/3 c times x to the 1.5 power, right? And we know that x squared should rise faster after some point, and x to the 1.5 power should rise faster at first. Whoops, I apologize. It's going to be kind of difficult for me to draw a curve here, but hopefully I can get it. Both obviously should start at 0. So let's say that this is going to be it for spring Q, right? That's our 1.5 power. Right, so let's label that spring Q. And then for spring P, what we might expect is something along the lines of this, right? So that one's going to be spring P on the left at that top. Now, I think what College Board is going to look for is I think they're going to look for a couple of things, right? First things first, do you have the correct trends there? I have x squared for spring P, 1.5 for spring Q. That makes sense, again, based on the integration of force with respect to distance. And I think what you're also going to have to do is you're going to have to show that spring Q actually has more maximum height to start due to that more work done, because the area under the force position graph is actually larger as well. And then for spring P, right, you would expect it to intersect for the maximum height at a point where x is greater than 0.04, because that supports our answer for part B as well, too. Good. So that's it for part B then. We can go ahead and move on to the next page. And on the next page, so let me go ahead and actually change back to my mouse here. So on the next page, right, what we do have is another situation now where we have two blocks. Block B is not yet compressing the spring, and then block A is at the very top. And what we want to do is calculate the velocity of the two-block system immediately after the collision. How do we do this? Well, this is a classic energy momentum problem right here. So I would say that UG is equal to the kinetic energy of block A at the bottom of the ramp, right where it reaches the bottom. So that would imply that MAGH is equal to 1/2 MA VA squared. Now, this isn't the speed that we are looking for, but it does give us a value that we are going to need when we apply conservation of momentum during the collision. So VA is going to equal root 2GH, and root 2GH is going to give us 3.87 meters per second. I've already done this math. I was taking a look at these questions a few minutes ago, right? But you can go ahead and try that out yourself as well. You're given the value for H as well. Now what we have to do is we have to do conservation of momentum. So we'll have MAVA is equal to MA plus MB, because they stick together, right? They're going to add their masses times the final velocity. Therefore, the final velocity should be 0.12 kilograms times 3.87 from our previous step, divided by the total mass, which is 0.19 kilograms, giving me a value of 2 point, I believe it's 2.44. I can't read my own handwriting, but I think it's 2.44 if I did that math correctly. If not, it's 2.94. Let's see. Oops, there we go. Good. Perfect. Now we have to calculate the maximum compression of the spring. How do we do that? Well, we know that after the collision, energy is conserved. So what I can say is that we have kinetic energy after the collision, right? 1/2 MA plus MB times the velocity we just computed squared. And that has to equal, because this is spring Q, it's not going to be 1/2 kx squared. It's going to be 2/3 cx to the 3/2 power. And we're trying to find x, of course, right? The maximum compression. Therefore, if you solve this for x, you get that x is equal to some very nasty numbers, right? 3 times the sum of all of the masses, ma plus mb, times vf squared. Again, vf is the 2.44, not the 3.87, all over 4c. And that's not it, right? There's also a power on x, 3/2. So you take all of that to the 2/3 power. Talk about a bad number, right? What you should get is a compression of 0.12 meters. Once you plug in c, right? C is actually 20 newtons per meter. That was given to us on the previous page. Again, we have the masses on this page, 0.12 and 0.07. And then we do have final velocity of 2.44. All right. Moving on to part D. In part D, it asks us which one's going to have the higher spring constant for spring Q or spring R. And I would actually say that spring Q should have the higher spring constant. And I'm actually going to go ahead and type this one out with text as opposed to writing it, because I think that'll take a little bit less time. What we know is we know that energy is conserved during the compression of the spring. Right, we used that in our previous part. So from the formula shown in C part 2, right, we know that x for both springs should be inversely proportional to C or D, right? So therefore, if x sub r is greater than x sub q, right, that would imply that C has to be greater than D. There we go. And that is it for question number 1, right? Nice kind of easy energy momentum question, not too difficult. There's a little bit of like work done as well, but honestly, probably the easiest of the 3. I definitely struggled the least with this one. So good. All right. Now we can go ahead and move on to question number 2. Question number 2 seems pretty nasty, but it actually is not as bad as I originally thought it was going to be upon reading it. We have a torsional pendulum made of n uniform disks. We're given the moment of inertia, the torsion constant, and basically we're going to be stacking up until n disks. So what the first question asks us is to actually use the equation, right? It says to use t is equal to 2 pi root I over kappa, derive an expression for t in terms of n. Now, the first time I solved this, I was actually thinking about using net torque, but that's because I didn't read that you have to use the equation that they provide to you, right? Well, in this case, we know that the inertias are going to just stack together if you have n rods. You should just be able to add it. So you're going to actually get that the inertia, that the period should just be nmr squared, right? Because you have n disks over 2 kappa, all multiplied by 2 pi on the outside and square roots. That is probably just going to be 1 point. I doubt you're going to get many other points for that. Good. But that does take care of that part. Now, if we go on to the next page, it's actually asking us to sketch a graph for the maximum kinetic energy as a function of n for n greater than or equal to 1. So let's mark n is equal to 1 right here. And I do claim that this should actually be an inverse relation. I do claim that k should be proportional to 1 over n. Again, forgive my bad drawing right here. It should have an asymptote at k is equal to 0. But the reason I claim that this is true is because so you're going to have the same net torque in all of these different cases, right? In all of the cases, you would expect the torque to look something like minus kappa times theta, right? Or kappa delta theta. And so in terms of that, what we would expect is that as you increase the number of disks, right, the angular acceleration would actually go down. So how would that happen? Well, we know that angular acceleration goes like torque over inertia. So therefore, what you can expect is that if you have torque over inertia, then if you have the same torque and you have again inertia like that, that's going to be proportional to 1 over n. Right, so that implies that the angular velocity is going to be proportional to 1 over n as well. And so therefore kinetic energy, which goes like 1/2 I omega squared, is going to be proportional to n from the inertia and proportional to 1 over n squared from the angular velocity squared. and therefore that should be proportional to 1 over n in its entirety then. So you have to think about both of them, right? How does changing the inertia change kinetic energy? And how does changing inertia affect the angular velocity or the angular acceleration as well, too? And you should find that it should be 1 over n. And that makes sense in the sense that like you would expect more massive things to move quite a bit slower as well, too. Good. Let's go ahead and clear this, and let's go ahead and move on to the next page. All right. Next page asks you to draw a best fit line for the data and to use your slope. For drawing a best fit line, you know, given that I'm on a computer, I can kind of like I can kind of like make this a little bit simpler, right? Because I don't have to actually use a ruler and a pen or something, but it looks something along the lines of this, right? You should not put it through 0, 0 because you're not given 0, 0 as a data point. All right, now we actually have to use the graph to calculate m if we know r and kappa. How do we do that? Well, on the first part of this problem, we said that t was equal to root 2 times pi multiplied by r times root m over over kappa times root n. And I know that's a lot nastier than the expression I have on the previous page, but the reason I made it nastier is because now I can say that the slope is going to be equal to t over root n, and that should all equal root 2 pi r root m over k. Therefore, if I solve for the mass, right, if I solve that for the mass, I should get that the mass is going to equal kappa over 2 times slope over pi r all squared. And if I calculate the slope, you're all going to have a slightly different slope, but I used the data points 2.2 and 0.6 and 1.7 and 0.45. And what that actually gives me is a slope of 0.3. So if I compute all of that out with my values of kappa and r, what I end up getting is 0.18 kilograms. 0.18 kilograms. All right. If you have a lower mass of the disk, right, if you find that you have a lower mass of the disk, right, then that is going to be, let's see, so the value given by the manufacturer is less than the value experimentally determined. So our experimental value of mass is higher. And what that would actually maybe require, and I'm not 100% certain on this, but I think that a reasonable explanation for this one would be if the string was thicker than expected. The string was thicker than expected in our experiment. The reason I think that that would work is because this would cause the inertia of the system to increase. And if the inertia actually increases, what that should do is that should actually increase the period. That would increase the period. Increasing the period, as we showed in the previous part, is going to therefore increase the mass because the mass is proportional to slope. Therefore, increasing our experimental value of mass. Good. And I think that that's a good description. You guys might have had different responses for that. Obviously, that's fine. College Board will take that into account when they actually score it. All right, now comes for probably my least favorite part of this entire FRQ, entire FRQ set, right? Now the disks have a density that is varying, like rho is equal to 0.3 times r. Would the slope of the best fit line be greater than, less than, or the same as the slope computed previously? And likewise for part 2, what would be true about the maximum angular speed for the uniform versus the non-uniform disk? Yeah, and so what I actually found is I did find that the second bullet point should be correct for both of them. So less than, right, for the non-uniform, and then the speed should actually be greater in the non-uniform as well. The way that I actually found that, and again, I'm not 100% sure on either of these, so if you've found something different or if you think that your answer is correct, please let me know in the comments as well. You know, I'm always trying to learn something as well from these too, and I do find these questions to be quite difficult myself, despite being so well versed in physics as well too. So it is something that I would like to learn if possible. So, kind of thinking a little bit about my solutions to these, what I would probably say is that the reason I say that the new best fit line would actually be lower slope is because I found that the mass is lower. The mass is lower for the non-uniform disk. And how did I actually do that? Well, I said that the mass itself was equal to the integral from 0 to capital R of the mass density with respect to area. Now, because these areas are circles, what that would actually end up looking like would be 2 pi integral from 0 to capital R, where R is 0.2, of R squared times 0.3, right? You end up getting an extra R from the dA, and then you get an R from the mass density as well. So that with respect to R. And if you go ahead and actually do the integration out, what you end up getting is 2 pi times 0.1 times 0.2 cubed. And that gives you a value of 0.005 kilograms. Therefore, lower mass, right? What we found earlier back on the previous page, lower m implies lower slope, right? The slope is proportional to mass. From part C. Good. All right. So if we do take a look at part 2, you can actually apply a similar thing, right? You have a lower mass, so therefore you would expect the inertia of the non-uniform case to be lower, right? I non-uniform is less than I uniform, right? Because both disks. All right, and I'm just going to move to typing because it's faster. Because both disks experience the same net torque, right, due to the torsion, due to the restoring torque, right, you would expect that the lower inertia case will experience a greater angular acceleration and therefore a greater maximum angular speed. Good. And I think that that is correct. I could see an argument saying that they would actually both have the same angular speed, but do keep in mind too that kinetic energy, right? If you're thinking about this from a momentum perspective, you would certainly get that they would be the same. But keep in mind that they do not experience the same torques for the same amount of time. The disk with more inertia is going to move slower, and therefore it should actually you're not going to be able to necessarily determine the correct answer with thinking about momentum. You have to think about this from a torque and angular acceleration perspective, or you can also think about this from an energy perspective as well too. But I am pretty convinced that it should be the uniform is going to move slower due to it having a higher inertia. All right, and so now we can move on to question number 3. All right, question 3 is a fun one, right? Rod swings downwards, hits a sphere, and stops. So that's good. If the rod didn't stop, we'd kind of be in trouble. Derive an expression for the angular speed of the rod just before striking the sphere in terms of the length and physical constants as appropriate. So what we do have is we do know that MGL, right? We do know that we have to track the gravitational potential energy of the center of mass because that's where gravity is said to be acting on, right? So the final potential energy isn't 0, it's MGL over 2. So we would get 1 half I omega squared plus MGL over 2 is equal to MGL, right? Therefore, you end up with MGL over 2 is equal to 1 half times 1/3 ML squared omega squared. Right, and then if you solve that for omega, you get the square root of 3g over L. Not too bad, right? There's our answer. Derive an expression for the linear speed immediately after colliding with the rod. This is a collision problem, so you would expect that the angular momentum of the system before the collision is going to be equal to the angular momentum after. before we have a solid object. So what I would say is it's easier to use I omega, right? And then after, you can think of the sphere as being a point object because r is much less than L. So that's going to equal Rm v naught. So if we plug in our equation for inertia, we're given 1/3 times 2 lowercase m times L squared is going to equal, sorry, I forgot the angular velocity, root 3g over L, right? All of that is going to equal L m v naught. And if you go ahead and solve for v naught, you should find that v naught is going to equal 2 times the square root of Lg over 3 then. Good. And that should be your final answer, 2 root Lg over 3. All right, next one is kind of tricky, right? It says that the sphere begins rotating without while sliding, and then after that begins rolling without sliding at point B. So what we have to do is we have to draw a rigid body diagram. Well, friction is going to cause it to actually start to rotate, so I would expect for kinetic friction to be pointed to the left and acting at the point in contact with the ground. Right, you've got normal force, which is equal to the weight force. Weight force does actually end up acting on the center. Normal force acts at the point in contact. There you go. There's our free body diagram. All right, part D, derive an expression for each of the following as the sphere is rotating and sliding. For linear velocity, what you would want to do is you would actually want to say that the change in linear momentum of the speed, so F net times t, is going to equal the mass of the sphere times the change in velocity. So the change in velocity is going to be v minus v naught. Well, the net force in this case is just friction. So what I would say is that we have mu times the normal force times t is going to equal m v minus v naught. Well, normal force is equal to mg. So mu mgt equals m v minus v naught. Therefore, v is going to equal mu gt plus v naught. There you go. All right, now I'll find an expression for angular velocity. Well, angular velocity, we can say that the sphere is going to be rotating around the center. So we could now say that delta L, the change in angular momentum, right, which is equal to net torque times time about the center, is going to equal the inertia of the sphere times the angular velocity. The angular velocity initial is 0. So it's just going to be omega minus 0, or I times omega, right? So the torque is caused by friction again in this case. So we have R mu mgt for torque times time, and that's going to equal 2/5 m r squared times omega. Therefore, omega should equal 5 mu gt divided by 2r. 5 mu gt over 2r. All right, let's move on to the next page. Next page, we got 2 more parts, and this one kind of stumped me, but I think I know how to solve this. It took me a few minutes, though. Derive an expression for the time it takes to get from point A to point B. Well, when we get to point B, the sphere is going to be rolling without slipping, so we know that V has to actually equal R times omega. We found expressions for V and omega in the previous page. We do know that V is equal to mu gt plus V naught, and we do know that omega is going to be equal to 5 mu gt over 2r. So we can go ahead and cancel the r's, right? We can move all of the t's over to one side, and we should get 3/2 mu gt is equal to v naught. So therefore, t should equal 2v naught over 3 mu gt, 3 mu g, excuse me, 3 mu g. All right, oh my goodness, that is a terrible square. I'm so sorry, guys. 2v naught over 3 mu g. Derive an expression for the linear speed, linear velocity upon reaching B in terms of v naught. Well, we know that, again, v is equal to mu gt plus v naught. So plugging in our expression for t from above, right, that should give us mu g times 2v naught over 3 mu g plus v naught, and that's going to give us 5 v naught over 3, and that should be the linear speed when we reach point B. All right. And that does it for set 1 of the mechanics FRQs. Let me know how you think you did down in the comments. Again, if you find anything that you disagree with, definitely feel free to let me know. If you found this video helpful, let me know as well. I am hoping to do set 2 pretty soon, and then also the E&M questions. So I'll try to get those all up as soon as possible. And yeah, thank you guys for tuning in. I hope that you did find this helpful. Have a good rest of the day then. And I'll see you guys in the next video. Take care.